Yeah, just for the recording purposes, I'm just giving a recap again. So today's class is going to be on unsupervised learning. If you are trying to find patterns with answers where you already know the answers, it is supervised learning. If you're finding patterns without answers, then it is unsupervised learning. So that is the difference between supervised learning and unsupervised learning. For supervised learning, you already know the end result, your target, and what you are looking for. In unsupervised learning, you don't know what you're looking for, but you only want to look for the patterns in the data and outcomes. And unsupervised learning is used in the places of customer segmentation, where you are trying to figure out you are trying to group the customers into people who are buying groceries, who are buying technical products, who are buying dresses and all. Fraud and anomaly detection from from spams and all, and credit frauds. Document grouping, any image compression, recommendation processing, anything that is related to grouping or clustering can be done using unsupervised learning. Think of, Monish, what is clustering? Think of clustering like an organizing a massive library where the books have no genre labels. It's like a very big library. The books are scattered all around. You have to group them by looking at the similarities in the text. You have to read those books. You have to understand what genre it belongs to, and then you will be segregating those books into different groups. That is the classical example of unsupervised learning. Dimensionality reduction is like taking a 1,000-page book, writing a 10-page summary that still captures the exact same plot. All of these are behavioral patterns. All of these are classical examples of clustering, grouping. Yeah, the difference between unsupervised and supervised. In supervised, target label is present. You exactly know what you are looking for, and there is an outcome column. But in unsupervised, you don't have a target label. There is no outcome label. You know the main goal in supervised. The main goal in supervised is to predict the outputs. The student will pass or fail. What will be the income? What will be the future sales? All of this is prediction, one or the other form of prediction. But here you are not predicting. In unsupervised learning, if you take the example of library, where you're grouping the books into a particular orders, you're not predicting, right? You're just finding the hidden structure. What is the one thing that groups all these books? You're trying to find the connection between those books. That is a classical example of unsupervised. You'll find the hidden structure. And in supervised, one of the widely used algorithms are linear regression decision trees that we have seen. In unsupervised, some of the commonly used algorithms is k-means. K-means, PCA, hierarchical clustering. These are some of the widely used common algorithms. And coming to output, usually the output in supervised will be a class or a number, pass or fail, low, medium, high. These are all classes. Either it will be a class or a regression. We have done regression project, right? For sales prediction, we will get a number as an outcome. But in unsupervised, usually the outputs will be in the format of clusters, components, or latent structure, which we are going to see in today's project. We are going to do a project. We are going to see how the output will look like. Yeah, clustering, I already told you what clustering means. Clustering is like groups. We are trying to form a groups similar that points together to a common point. It should have a common point. Points inside one cluster should be more similar to each other than points in other clusters. Example, if you take two groups, if you take a group of sheeps and if you take a group of cows, two different groups, two different animals, then the differences should be huge. That is what clustering says. Sheep all should have a common point. Cows should all have a common point. You cannot say there is only little bit of difference and you cannot just put the clusters. There has to be a unique point to them. For a group of sheep and group of cows, there has to be a unique identification, unique point that separates both of them. This is an example that I thought. grouping shoppers by income and spending behavior, even we do not know their segment names in advance. So there will be people who spends 8k 10k on shopping. There will be people who spends only 500 or 1000 1k in shopping. So this is the basis. Even before the person buys anything, based on their income data, you can segregate them. This is one of the example of clustering. Yeah, till here, any doubts, anyone? Okay. Yeah, all clear, right? If any doubts, yeah, please let me know. Okay, what is k-means, Monish? So k-means is one of the popular algorithm that we will be using throughout in when we are learning about unsupervised learning. Uh, so k-means is the workhouse of clustering. I say workhouse of clustering. It's iterative. It makes a guess, measuring how bad that guess is, and shifts its center of gravity. Example. Uh, Let me open whiteboard. You have a few animals. Let's say you have few animals: cow, sheep, tiger, lion. Okay, and you also have few more animals like uh, let's say crow, sparrow, parrot, pigeon. We are giving this to AI now. We are giving this to AI and we are telling to segregate. We are not telling anything. We are not saying anything. We are just telling the AI to segregate. Just segregate. Okay. Based on what we are not saying even. We are just telling to segregate. Now, the k-means will look at all these animals. We are providing the names and we are also providing its characteristics. We are providing the characteristics of each one of them. Now, what it does is like first it will how k-means works. I'm telling you. So first, let's say k-means will take a guess. It will guess. It will take a guess. It will put cow and pigeon together into a group. It tries to it first puts them in a group and it tries to understand the attachment, the connection between these two. Then it comes to know, okay, so cow is more related to sheep than a pigeon. It comes to understand this point. First it guesses something, then it tries to find the score between them. Cow is more related to sheep than pigeon, so it removes pigeon and it puts sheep. Now, again it checks for the connection. We have cow and sheep now. Again it checks. Cow, sheep. So is it connected with the tiger? Is it connected with lion? Is it connected with crow, sparrow, parrot, pigeon? It tries to look the patterns. Suddenly it finds a characteristic that cow has 4 legs, sheep has 4 legs, tiger also has 4 legs. So it brings tiger inside. Then again it looks. It also finds lion. Lion also has 4 legs. So it puts lion inside this. In the same way, it iterates, and suddenly it will try to find some patterns. Now you came and you said to the AI that you want to divide this entire kingdom, animal kingdom or something, into a clustering based on their food, based on whether it is carnivorous or herbivorous. You want to just do a clustering based on this thing, what we say, food. So already AI knows its characteristic, right? It looks what cow eats grass and all. It's herbivore. So it starts with cow, then it looks for the next herbivorous animal, sheep. It goes to tiger, so it's not a herbivore. It goes to like not a herbivore. It goes to crow, sparrow, parrot, pigeon. If any one of them are carnivorous, it just removes them, and it creates the clusters, it creates the groups. That is how your k-means works. It first, the k-means works like it makes a guess. It measures how bad that guess is, and it shifts its center of gravity to a different different guess. But the hardest part isn't the matrix. It deciding how many clusters k we want to begin with. If the more the clusters, Monish, what is this number of clusters? The more the number of clusters, the more the grouping, the more the what do we say, the more individuality. How do I usually teach the number of clusters is, with this example I think you'll understand it better. Let's take this world. This can be a life lesson also. Let's take this world, this entire world. Okay, if I say my clustering is 1, if I say my clustering is 1, I want only one color cluster. If I say that, then world is one. World is we are entirely united as a world, earth. Okay, earth. When compared to solar system, when I say k equal to 1, clustering only one clustering, then I say the example is earth. We are all united because we are on earth. If I say k equal to 2, now the clustering gets divided. Now the grouping gets divided. Now suddenly we say continents. If I say k equal to 3, now suddenly earth is divided into continents. Now continents again I divide it into countries. Now if I say k equal to 4, that is further separation. For countries again I say states. Next, if again I keep on going like k equal to 5, then states also will be further divided into places or regions. If k equal to 6, sub-regions. If k equal to 7, then streets. You're getting my point, right? The lesser the k value, the more the better the grouping. I mean the what do we call, less individuality. If I keep on increasing the k, value, then that entire big group is further divided into smaller subgroups. That is what k here stands for. Like you have to determine how many clusters of k you want to begin with. The more the cluster, the more the more sections of grouping is gonna be performed. So you have to keep that in mind, how complex your grouping you want it to be. Yeah, any doubts still here?
Yeah, I'm following through because I think I've used all these in the past.
Okay. Um, Okay. So yeah, it how k-means works. It chooses the number of clusters we have to use, randomly initializes the centroids, assigns each point to the nearest centroid. Each point to the nearest centroid in the sense the connection, how strong the connection is, how low the connection is. It recalculates the connections between each of them, and it repeats until all of the connections patterns make sense. Until all of that makes sense, it just repeats itself until everything is grouped into something. These are some of the k-means strengths and weaknesses. Uh, k-means is fast and also easy to explain, like how I explained it, easy to understand. It works well on compact clusters, scales well for many rows, for many different use cases, and it's also a great teaching algorithm. So that even for teachers who wants to teach, it is easy to easily teach that. Some of the limitations, as I said, it's you have to choose k. If you are choosing k, there might be a problem that you are making. Instead of for example, you're trying to find the caste or something like that, which is more into subregions, and you cannot put k equal to 1. You cannot put k equal to 1, and you cannot expect your algorithm to uh, divide humans under the basis of caste or religion. You cannot do that. If your k equal to 1, already humans all are united as people, that they all belong to a particular planet. They are all united. You cannot separate them by religion or caste if you are using k equal to 1. You're getting my point, right? You can only divide them if you're using a higher k value, like k equal to 7 or k equal to 6. Then only you can start divide the humans. So based on your use case, you have to come up with proper k value, how many clusters you need, how many grouping you need. And it is sensitive to scaling. So when the uh, what do we say, when the scale increases, for 1,000 people the algorithm works in a one way. For 10,000 people it works in a different way. For 1 crore people, then suddenly it has to look for lot of patterns, because things get more complicated in finding patterns and relationships. When the more the number of people increases, and just I mean people in the sense, I'm just giving an example, anything on anything. When anything the quantity increases, suddenly there are a lot of complications also occur. So it is very sensitive to these kind of complications, sensitive to outliers, sensitive to scaling. And it's not ideal for irregular cluster shapes. What is an example of irregular cluster shapes? Yeah, one of the example that I can think of is usually we have two genders, right? A male or a female. Then suddenly we have a third gender. So still now here it is fine, but suddenly there are a lot of genders that are coming up these days, which are impossible to keep track of. So that is one classic example of irregular cluster shift. You cannot just put them. You don't even know the pattern. As a human, even we don't know the pattern. How will a machine know what the pattern looks like? So that is one classical example of irregular cluster shifts. You cannot just put them in any of the category. Yeah, this is as I said, that as there is a limitation of k value, right? So Monesh, how do we overcome this choosing the k value? So there is something called elbow method in k-means clustering. We can use that elbow method where we plot inertia of several values, like taking a mean or something, and we use that for the k. When we do the project, I'll tell you better. And there is also called as Helmholtz score, measure how well separated clusters are, like how well your separation needs to be. And we use metric plus domain understanding. That is where we cannot be only technical. For example, if you're running a supermarket, you should also think of human side of the things. That is domain understanding, not only metrics alone. Okay. This is a complete, as I said, this is a prototype that I've designed. This is like 41 slides. I cannot go over all the 41 slides in this. But yeah, I will send you this HTML. Now we will start with the actual project that I'm thinking of. Yeah, let's go to collab. And I'm not gonna super complicate things. So for unsupervised learning also, you can do a lot of complex things and all, but I'm not gonna overcomplicate for today. And I'm just looking for that Kaggle dataset. Customer segmentation. It's a Mall customer segmentation. Yeah, this is what I thought. So we will be using Mall customer segmentation data. Monesh, why are we using this particular column and why not the others? One of the easiest way to explain again, today I'm taking a very easiest route, a comfortable route, not like yesterday. Just to make things easier, just to make this class a complete comfortable class, I'm taking this route. And I really doubt you will be using unsupervised going forward a lot. Most of the times you will be working more on supervised. And deep learning, then we go for agentic creation and also unsupervised has less scope in our course. And one of the easiest way to teach someone or to do a project on unsupervised learning is Mall customer data. That's it. It is Mall customers data. Very easy to do. The code itself becomes so easier because you have only few things: annual income, spending score. That's all. Only 5 columns we have. I have seen other data sets also which have 13, 14, 16 columns, but I picked this one to make things easier today. Only 5: customer ID, gender, age, annual income, spending score. We're gonna take this annual income and we're gonna take this spending score and we start to do the grouping. This data set has around 200 rows. I've already seen it before the class. It is 200 rows, 5 columns. So simple data set, uh, easy to work on. I'm sharing the data set into the chat. Okay. Before me importing, actually, let's first import the data. That makes more sense. Download path. Click on
Munish,
Yeah, yes.
can Or you're already sharing the collab file, or
Oh no, I'll share the collab.
okay, thank you.
Yeah. Yes. So runtime, change runtime, GPU, save. Okay, the file got downloaded to Kaggle input customer segmentation tutorial in Python. So let's see if it really got downloaded. Kaggle input. No, it's not. Again, this happens to me, but for Kamala, it was working in the other class also. Yeah, now I have. You can see here. It got downloaded and it got stored. Now let's start with the code part. Okay. As usual, let's import all the libraries that we are going to use in this particular project. Obviously, we use pandas every time. And I don't have this project pre-built. As I said, this is a last minute change that I've done. I have already have a deep learning project that I was working weekdays to show it to you. But yeah, I don't have an unsupervised project ready, so I'll be doing the live coding. Even I don't know what I'm gonna do. When I'm doing, I think and I do. So yeah, let's bring out all the libraries that we may need for this project. We need pandas, we need NumPy. What we need? We need matplotlib, we need seaborn because I have to show you plots in supervised unsupervised learning. Next, algorithms from scikit-learn dot all the cluster we get from scikit-learn dot cluster. So I'll show you k-means. K-means is for sure very important algorithm, and there is also something called agglomerative clustering. Let me show you that as well. Agglomerative clustering. We have StandardScaler. StandardScaler is for pre-processing step. We also need to have a silhouette score. Silhouette score is for the metrics to find out how good the grouping is. We need PCA for decomposition. Yeah, and also we need. I have to show you cluster hierarchy. So from scipy, I think it comes from scipy dot cluster hierarchy, dendrogram and linkage. This is just to visually show you the interaction, the connections between different rows or different things. Just to visually show you, I am using this. Yeah, this will be fine. We already have the data, but you have to put the data, right? Df equal to pd dot read csv path plus Mall Customers csv. Yeah, the data is loaded. Now we start our usual thing. The what do we say? Df.info, df.describe and all. But before doing that, if you observe these columns, annual income space k dollar symbol. This dollar symbols are there, right? It may create a problem when we are going further in the project. Always clean your columns, because in the job and all, you will see columns like, for an example, customer underscore region underscore uh, labeling labeling hyphen k1028 hyphen 3246 hyphen. There will be some secret codes for the columns. So when you're working with those type of columns, I would suggest always to clean them up, because you cannot keep on writing those big column names every time. So I would suggest to first rename. Df dot rename columns. Yeah, annual income is a good column. Spending score is also a good column. This is fine. And in place equal to true. Yeah, now see, it looks neat. Customer ID, gender, age, annual income, spending score. And we should know that they are in dollars. This annual income is in dollars. Spending score is from 1 to 100. How well they're spending. 100 means they're spending more money. 1 means they're spending less money. If you see, okay, it is k, it is in thousands. It is 15k. It is 17k. $17k. Okay. So as usual, we do df.info and df.describe. Okay. Info is good. Describe is also good. You can find the max. Max is 137k. This can be an outlier moving forward. Again, I don't know nothing about this data. I don't know nothing about this code also that I'm going to do now. I'm making few assumptions because if you see, all of the annual incomes are in 15, 16, 17's range. But suddenly you have a maximum of 137 and the mean is 60. Definitely this is an outlier. The mean is 60k and you have a maximum person who is earning 137k. Yeah, this is an outlier. We have to take care of this later. That is why we use df.info and df.describe. df.info tells you the data types. What are the data types you have on the columns? df.describe tells you, gives you an overview of your entire data. What is the maximum? What is the minimum? What is an average? And all. See, the minimum person who is earning is 15k. The maximum is 137. So you will be planning accordingly. And the maximum person who is spending score is 99. 99. In the sense, he is spending all the income in the store itself. Like if he is earning 137k, he is spending 135k in the shopping. So this also can be an outlier because if you see the mean is only 50. If the mean is 50 and the max is something around 99, that shows this person is somewhat an outlier. He is an exceptional case. We have to take care of this data. And the minimum is 1. Okay. Yeah. Any doubts still here, anyone? Okay. So let's start with our basic EDA. By EDA in the sense exploratory data analysis. Basic stuff. So in EDA, what do? We see that if there are any null values, we remove them and we do plots. Are there any null values here? No. In none of the data, there is no null values. No, non-null, everything. So what is the next step? We have to do the plots to better understand the data. Monish, why are you giving only 15,4? 15, row in the sense 15 rows of space, 4 spaces of column. Monish, why are you giving this 15,4? There is no rule. You can give anything. You can give 10,4. You can give 10,6. You can give 10,10, 0,4. However you want, you give. I like to give 15,4. I like because since my the monitor that I'm using has more of horizontal space than the vertical space. So that's why I'm allocating more space to my horizontal, that is rows to 15, and less to the vertical thing. So this is an ultra wide. So I'm putting my fixed size so that my outputs will be clean to show it to you. However you want, you can change it. plt dot subplot 1, 3, 1. Okay. SNS. First, I'll show you histogram plot. Histoplot d of h bins. I'll show you what is bins mean. Bins 20. There is a parameter called a KDE to be true. Again, this is optional. If you want, you can remove it. Just it makes the the plot more appealing to see. Age distribution. Yeah. Okay, this looks neat. Yeah, you can see the age distribution around the data. The more the people who are more, not spending more, but in our data, the more number of people that we collected the data are higher in 30 to 40. In the middle of 30 to 40, we have more number of people in our data. ELT dot subplot. You know why I did this? Why I did age distribution? The basis on why I did age distribution is because, for example, if our data has more of adults in the sense senior adults, let's say 50 to 70, then usually they buy more of products they want for senior adultery, right? Like medicines and all. So then I say that the data is not a good data because you are just putting more emphasis on senior adults. And for example, if our data only has children in it, then they'll be buying toys and all. If our data more of maybe 20 to 50, 20 to 40, they will be buy more other things like groceries and technical stuff, TV, laptop, these kind of things. So usually our data has to be distributed in all the ages. Then only we say it is a good data. Here, this data is fine. It is not categorizing to senior adults, but I also can understand because some regions, senior adults usually don't go to buying products and all. They do order online, or usually their kids take care of them. So I can understand why senior adults are not putting more effort to come and buy products. This makes sense. In an outer layer, this data makes sense. Next is annual income distribution. Okay, this also seems nice. Yeah, this also seems okay. So the same thing. You can do the histoplot for spending score distribution and all. Let me show you some different plot this time. Tight plot. Sorry, tight layout. ELT dot show. Why it is not showing? There is a plot called tight layout. I just want to show it to you. It doesn't need any parameters from what I know. Okay, got it, got it. I set here 3, 1, 3, 1. So 3 plots I have to do, but I did not give the third one. Yeah, makes sense. Yeah. Okay, you may be wondering what happened here. So let me bring this down. Yeah, now it got. Okay, the mistake is mine. So I thought of showing all these three at a time at the end, but that doesn't work like that. I have to put all of those things into the same cell. Only then only I can show multiple plots in the same output. So what this is one more type. If you want to show 5 to 6 or any number of plots or outputs as a single output, if you want to combine them and if you want to show them as a single output, then you use this code. Here I mentioned subplot 131, right? 131 is this one. So row, one row, three columns, and in that, the first one is age distribution. The second one is annual income distribution. The third is spending score distribution. That is how it works. That is this plot dot subplot I am doing from the beginning, so that I can put more number of plots in this. If I want 4 columns, let's say I want another plot at here in the right side, then what I do, I put 1 comma 4. Okay, 1 comma 4, 1 comma 4, and I add one more here, 1 comma 4 comma 4. Instead of spending score, let's take what we have, gender. Let's take gender. Gender distribution. See, now you got 4 because one row, 4 columns, 1, 2, 3, 4, 4 columns. So that is how it works. Yeah, any doubts still here? Okay. Yeah. So plots are done. Oh yeah, pair plot. SNS dot pair plot. Pair plot is also important. For pair plot, I think all are not required. DF age, annual income, spending score. Oh yeah, right. So we are using multiple, right? So I have to put one more. Yeah. So these are different plots showing the connection between all these 3 columns. So age and annual income. This is how they are scattered. This is how the data is scattered. For spending score and age, this is how the data is scattered. So a visual representation between the connections. Next, we do the feature selection. Feature selection very simple for this data set. Only 2: annual income, spending score. That's all. Annual income, spending score will be our feature selection. Based on only these two, we are trying to create groups. Okay, next we have to do is scaling. I'm just thinking how to teach you scaling here. So before we run any clustering algorithm, uh, we need to scale our features. We need to scale our features, and this is one of the important step that many beginners skip, and it will cause problems later. Uh, Look at this line that I'll write now. Scalar equal to scalar dot fit transform of x. Yeah, correct. So we are creating a standard scalar object and then calling fit transformer on our feature matrix X, which contains annual income and spending score. What does this standard scalar mean, Monish? What it actually does? It transforms each feature so that it has a mean of 0 and a standard deviation of 1. This means every feature is now on a comparable scale. We already have done scalar in one of the previous projects, if you remember, but yeah, it has been a while, so you may forgot. So why we do this is the numbers from, for example, if you take this 39, 81, 6, 77, 40 and all, since this is only like what, how much data this is, like 200 rows. Let's take 200 million rows. 200 million rows, and you will have data scattered all around. You have zeros, you have ones, you have thousands, 10,000s, 1 million, 2 million, 25 million and all. When you have a way vast data data spreading across from various numbers and all, it becomes tough for clustering during pre-processing time. During your algorithm pre-processing, it becomes tough for the algorithm. So what we do, we convert this entire data into in between zeros and ones. I'll show you the data now, how it looks. It is scaled, right? X of scaled dot head. Oh, you cannot do head on it. Let's only put X of scaled. Yeah, you see what I'm talking about. So 15 is converted to minus 1.738. 39 is converted to minus 0.43. So what I'm trying to say is, we have already done this before. In one of the previous projects, I've shown you how to do this. But again, I'm telling you, it now for algorithm, this becomes much more easier to work on rather than working on 15, 16, 17 and all, the numbers 81, 6, 77 and all. It becomes much more easier. Monish, when I have to do scaling, Monish, if you're working on a very small data, you no need to do it. In this case, in our project, you no need to do it. That was the reason I took a pause after this. I was thinking whether I have to tell you about scalar or not. In this project, it's not required. This is completely not required. You can just remove this code if you want. But why I'm teaching you is, when you're working for a very big data set, like 200 million rows and all, the spread of the data is going to be huge. And when the spread of the data is huge, you have to do standard scalar. Otherwise, your algorithm will take hours, sometimes days to train the model, which you don't want to do. That much time you should not waste. So perform standard scalar. It creates a fit, converting your numbers from 0 to 1 ranges, minus 0 to 1 or plus 0 to 1 ranges. So 15 is now converted to minus 73899. So that is the reason, if you see, first two are 15, 15. These two follow the same name, same number, 9919, 9919. But the next one is 16, slightly it got increased. See, 16 is increased. So this is how you do standard scaling. Because again, I'm saying, because k-means uses distance to measure similarity between points. If annual income goes from 15 to 140 and spending score goes from 1 to 100, income has a bigger numeric range. It has a bigger weight. Without scaling, income would dominate the distance calculation and spending score. So we don't want that to happen, and scaling fixes and gives both features equal importance. The same thing we have done in supervised learning. If you take the supervised learning code, look for scaling. We have done scaling in it, and this was the same reason I have given on that day. One will be given more weight than the other if you don't do scaling. So any doubts still here? Okay. Next is the famous elbow method that I was talking about. When you don't know k, let's say Monesh, I don't know k Monesh. I'm gonna use k means clustering, but I don't know what I'm gonna use for my k. What is the k range? I don't know. You tell me how to find out. So if you don't know how many groups you have to divide and all, we need to figure out that. Now we need to figure out how many clusters to use. K means requires us to choose the number of clusters, which we usually call it as k, before running the algorithm. But how do we decide? How do we decide what k should be? This is what the elbow method helps us with. If you are going for an interview and if the interviewer asks you something related to unsupervised, 99% of chance he will be bringing up this elbow method. Without elbow method, there is no k-means clustering. I mean, that without that concept, you wouldn't have learned about k-means in the first place. So I'll show you how to decide on k. Inertia equals to an empty array. K range equals to 1 to 11. Okay, 1 to 11 is fine. I'll tell you the code once. Let me complete it, and I'll tell you what I'm doing. And clusters will be k. Random state is 42. Also, let's put n in it to be 10. K means dot fit is x scaled. Inertia dot append. K means no, it should be. Yeah, k means dot inertia. Yeah, this should work. Okay. So we start with an empty list called inertia. You can put any name to it. I put inertia. Then we loop through the values from k from 1 to 10. From 1 to 10. Huh? Monish, you said you wrote here 1 to 11, Monish, but you're saying 1 to 10. When you say range is from 1 to 11, usually 11 won't come. If you say range is from 1 to 100, 100 won't come. I want my range, I want my numbers from 1 to 10. I mean, the k, I want the k that I have to decide to be in between 1 to 10. That is what I want. My number of groups. So that is the reason I have used 1 to 11. 11 will not come, only it will go from 10 only. Till 10 it will go. So from 1 to 10, for each value of k, we create a k means model. We create a k means model. We fit it to our scaled data and we record the inertia. Inertia, how do I say? Like a result. We look at the result. We look at the relationship. Now, what is inertia? Monish, you're saying a lot about inertia. What is inertia? Inertia is the sum of squared distances from each data point to the nearest cluster center. There is a formula for inertia. Supervised learning. K means inertia formula. Yeah, this is the inertia formula. If you want to go into too deep into maths, this is what the formula is. But generally, it is the sum of squared distances of each data to its nearest cluster center. That is how inertia is defined. And this is the actual formula if you are interested. But you no need to, you're not going to write it in code and all. You will be just using k-means dot inertia and it will work. So when k is small, say k equals to 1. When k is equal to 1, all points are assigned to one cluster and inertia will be very high. As we increase the k, each cluster becomes tighter and inertia goes down. Actually, yeah, that's right. Sorry, when I'm teaching, I'm getting real life examples to my mind. So what I'm trying to say is when k value is low, the inertia is high. When k value increases, inertia decreases. You can think of a real life example where k is the individuality, not the individuality, unity. In inertia is the unity, k is the grouping. Very simple example that just came to my mind. Here in this example, k equals to grouping. Obviously, k equals to grouping. And your inertia here is, in your real life, unity. Unity. So when the k's value is less, inertia will be high. In the sense, when the k equal to 1, if we are all united as Earth, let's say there is no differences. Let's say I don't hate you, you don't hate me, and we are all united as humans who belong to Earth. Then we say that unity is very high because there is a lot of unity between the people, because they are thinking that we all belong to one particular planet and we help each other and all. But when you increase the k, unity starts to decrease. What do you mean by increasing the k? When you're grouping into subsections, like for example, you're grouping people on their which continent they belong or which country they belong. Like let's say you belong to India and I belong to America, and if you do this kind of separations, if you do this kind of grouping a lot, automatically unity starts to decrease. In real life also this happens. That just came to my mind when teaching this grouping and unity. So yeah, k is grouping, inertia is unity. When k value decreases, inertia increases. When k value increases, inertia decreases. They both are inversely proportional. Remember this. Yeah, any doubt still here? I'll show you a plot. Yep. You see here, you see this plot, right? Here the number of clusters, the number of clusters k is 1. When it is 1, it is the highest. When 2, it started to decrease. 3, it decreased. 4 decreased. 5, 6, 7, 8, 9, 10. So it is a pattern that you can see. Whenever k increases, inertia decreases. So we are plotting k on the x-axis, inertia on the y-axis. The curve drops steeply at first and then flattening out. The point where it bends, which looks like an elbow, is the reasonable choice for k. Monesh, why are you teaching all of this? It is to find the k. The place where it bends. The place where it bends is the k. It is the k. So here, and again, it is purely perceptual. You can argue with me, Monish. Here 3 is the bending point. I take 3 as the k. Okay, take 3 as the k. Monish, I feel like 4 is the bending point. I take k equal to 4. Okay, take k equal to 4. Where you think it is bending, where you think that might be the point where you know, people started to become too individual and less unity. That is the point where you have to take it as k. That is the best number of grouping. If you go beyond it, it starts to fail. It starts to become more individual. If you're going on the left side, if you're going on the top, it is too united. You have to find the sweet spot in between them. So I feel like 3 or 4. I think 4 might be good. Yeah, I feel like 4, but yeah, it's up to you. However you want, you do it. I think also 5 makes sense more than 4. Yeah, I think 5 makes more sense. I go with 5. I go with 5 because 4 is at the top here. There is no that difference between 4 and 3. 3 is 150. 4 is 100. Huh? No, 120 around, 110 or 110 around. But 5 dropped nearly to 60. Yeah, I take 5. My k will be 5, but however you want, you can do it. You can take k equal to 4. You can take k equal to 3. But I feel like 5 might be the right sweet spot, so I take k equal to 5. Yeah. Any doubts still here on how elbow method works and how we can find the k of k means clustering? Any doubts still here? Please let me know. Okay. Okay then. So as I said, I'll take 5. Next, we have to go is for Silhouette score. The elbow method gives us a visual hint. The elbow method is giving us a visual hint, but it is somewhat subjective. Sorry, just a second. Just a second. Just give me a minute. Yeah, sorry, someone was at my door. Yeah, where I am. Yeah, Silhouette score. So the elbow method gives us a visual hint. It gives us a visual hint, but it is subjective. As I said, I mean, now we discussed it, right? K can be 3, 4, or 5, and I took 5. You can take 3 or 4. It is very subjective. The Silhouette score gives us more quantitative measure of cluster quality. Here we are just talking about the perceptions. You can argue with me, Monish. I will take k as 3, Monish, and someone can argue k can be 4, and I can argue k equal to 5. But we don't know the right quantity measurements, right? The quantity measurements will be given by the quality of those measurements will be given by Silhouette score. How to find the Silhouette score? I'll show you. SIL score equals to, let's take an empty array for k in range 2 to 11. K means equal to n clusters to be k, random state to be 42, and int to be 10, and labels equal to km fit dot predict x of scaled score equal to score equals to slot score. Yeah, print uh, 1, 2, 3, 4, 5, 6, 7, 8, 9. Where is the 10th one? Oh, we are doing from 2 to 11, right? Yeah, I forgot. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct. So from k equal to 2 to 10, I have taken the scores. Now all you have to do is you have to pick the biggest one. So this is for 2. This is for 3. This is for 4. This is for 5. This is for 6. You see, oh, 5 is the highest one. You see here, this is 0.49, 0.46. This is for 2, this is for 3. Sorry, 2, 3, 4, 5. This is 5, 0.55, and this is 5, 3. Now it starts to decrease. Now the sill score starts to decrease. 5, 3, 5, 2, 4, 5, 4, 5. So the highest is 5. K, when you take k equal to 5, that is the highest one. So what we did here in the code is we start the loop from k equals to 2, not 1. That is because sill scores require at least 2 clusters to be meaningful. That is the reason I have taken it from 2. You cannot measure separation when there is only one group. For each value of k, we fit k means we get the cluster labels and compute the sill score. What does sill score measure is, for each data point, it measures two things: how similar that point is to its own cluster, and how different it is from the next nearest neighboring cluster. This is what the two things it will look for. The score ranges from negative 1 to positive 1, minus 1 to positive 1. A score close to 1 means the point is well placed in the cluster. A score close to 0 means it sits near the boundary between the clusters. And negative scores means the point must have assigned to the wrong cluster. That is what it represents. When we print the scores, we look at the value of the k that gives the highest slot score. Combined with the elbow method, this helps us to confirm the choice of k equals 2. In this case, the confirmed choice of k is 5. 2, 3, 4, 5, and 5 is the highest. So take k equal to 5 and you will get the best k-means algorithm model. Yeah, so before fitting the model, before finalizing the k-means model and putting the model, let's take a break. And we'll meet back after 20 minutes. And if anyone have any doubts, please let me know till here. Okay, I see no doubts. Yeah, let's meet after the break then. Yeah. So yeah, I stopped at fitting the model. Now finally we will use the k-means model and we will train it. Scaled. So we create k-means object with 5 clusters, since we set the k to be 5, and call fit predict. This predicts the model to the data and immediately returns a cluster label for every row. We store those labels as a new column called k-means cluster in our data frame. So the argument random state equal to 42, as we already know, it means set a fixed seed so that the results are reproducible every time we run the code. And the argument n int 10 means k-means will run 10 times with different random starting points and keep the best result. This is important because k-means can get stuck in the local optima depending on where the centroids are initialized. So and in it 10 is also important. And run the code. It has run. Then we plot the result. Annual income, spending score, k-means cluster. C map to be where it is. There are a lot of themes for C maps in Scatter. This is one of the theme. Yeah. So this is how the grouping done. That this is the grouping. As I said, this is how the clustering works. Now you can see here, this yellow data points are clustered in this manner. This is the second cluster, third cluster, fourth cluster, and the fifth cluster. So this scatter plot puts annual income on the x-axis and spending on the y-axis. Each point is colored by its cluster assignment. When this plot appears, we see that there are 5 distinct groups. Uh, this is the core. This is the core output of this entire project. And so you see different groups, like here the violet or dark blue navy blue group is the high annual income and high spending score group. This blue light blue is the less annual income but high spending score group. Middle is the medial annual income medium spending score. Like that you can differentiate different groups here. After fitting this model, we need to understand what each cluster actually represents. That is the job of the cluster profile. We are going to create a cluster profile now. Visually, you can see it. Visually, you can understand what is going on. But to put it in text, we do cluster profile. Yeah, we group the data frame by k-means cluster and calculate the mean age, mean income, and mean spending score for each cluster. Each cluster, not the person, each cluster. This gives us a summary table. For example, one cluster might have a higher average income and have a higher spending score. This is our premium customer segment. Another premium customer segment, in the sense, these are premium customers because their income is high, they also their spending scores are high. We treat them as premium customers. Another cluster might have a low income and low spending score. Those are your budget customers. Those are your budget conscious customers. So this step is critical because clustering is not finished when the model runs. Clustering is finished when a human looks at the numbers and gives the groups a meaningful name. A cluster number like 0 or 2 has no business value on its own. This but this interpretation has. Now what happens is like a real business, a person who runs, I'm sharing the screen, right? Just wondering. Yeah. So the person who is now running the store will be able to look at this scores and understand the visual cluster, and he can easily identify the premium customer, budget customers, and all. So till here, any doubts, anyone? Good. Okay, I got the thumbs up. Thanks, Komal. Yeah. So next, once this is done, right? As a business person, now I know who are the uh, premium customers, who are the budget customers. I came to know. This is the same thing that happens in Netflix. This is the same thing that happens in Amazon. This is the same thing happens in Prime and all. All the places. This is the same type of things happen. Now let us compare our k-means result with a completely different algorithm called hierarchical clustering. This is done. Our clustering is done. With k-means clustering, our project is done. But let me also teach you one more clustering called hierarchical clustering with linkage. And let's compare both of them. This is a new algorithm. Dendrogram we have imported, right? Oh, it's a spelling mistake. Okay, okay. It's a typo. So this is what I'm saying. This is one more the linkage function. Here I have used, right. This linkage function computes how every pair of points or groups should be merged based on the distance. We use some method called Watts method, which minimizes the total variance within clusters at each merge step. It tends to produce clean, well balanced clusters, and this is the visual representation on how it works. And dendrogram function, this one, this dendrogram function then draws the result as a tree, each leaf at the bottom. Actually, let me increase to 20. 20 also, I think it's not visible. Let's make it to 40 and see. Yeah, it's much better at least. So as you move up the tree, points merge into groups and groups merge into larger groups. The vertical height of each merge tells you distance at which two groups were combined. Taller bars means merge happened across a bigger distance. This is an example on what I was talking about, the earth, continents, countries, states, regions, and all, right? So earth is divided into multiple continents. Continents are divided into multiple countries. Countries are divided into multiple states. This is the visual representation. So how do you read a dendrogram? Look for a big vertical gap. Look for a big vertical gap. Where is the biggest one? Here, blue. Look for a big vertical gap, a place where this is a long bar before the next merge. Then it is a natural cut point where it is cutting here, then where it is cutting here, then where it is cutting here. So by that you will be looking on how it is being divided. Through the largest vertical gaps, you can estimate a reasonable number of clusters. And this thing, we will be putting it into something called agglomerative clustering, which I've imported in the beginning. This is a different model on how we have used k-means. This linkage, this agglomerative clustering gives you hierarchical clustering. This is a different algorithm. Aggregation equals to to clustering, linkage equals to what? So five uh, we use 5 clusters to match k-means and store results as a new column. And actually I can show you, but you also see it after the class. I want you also to compare both of them. Already comparison I've taught you in the previous classes, right? Use the same way, same code. You compare this model and that model. Same, it is the same code for supervised and unsupervised. That's why I'm not showing it again here. But you do the comparing. It's an assignment for this class. Same code, whatever the comparison code we have used in supervised, copy it, bring it here, paste it, use your agglomerative and use your k-means and compare it. Or else you can use Gemini also. It's a very simple code. I want you to try that. You just click on this button and ask Gemini to compare both of them. So this is done. I'm forgetting something to teach. Agglomerative done, k-means done, standard scalar done, sellout score is done, dendrogram is done, linkage is done, PCA. Yeah, PCA. I forgot to teach you PCA. Okay. Now let us look at PCA, which stands for Principal Component Analysis. PCA stands for Principal Component Analysis. PCA is not a clustering algorithm in the first place. Just to make sure, PCA is not a clustering algorithm. It is a dimensionality reduction technique. It is a dimensionality reduction technique. We use it here to visualize our data more cleanly. It is not an algorithm. It's not a clustering algorithm. Notice we now include age as a third feature. Till now we have used only annual income and spending score, but here we have included age as a third feature. This means our data lives in three-dimensional space, which is harder to plot directly. But PCA can do that. Now I train the model PCA x3 PCA dot fit transform x3 scaled. Yeah. So PCA takes three-dimensional and compresses them into two-dimensional, called principal components. Monish, what is going on? So till now we worked only 2 dimensions. One is annual income and spending score. If you scroll to the top, where is K means? Yeah, if you see here, K-means only taking two things, annual income and spending score. But now I'm taking three things, age, annual income and spending score. But it is really tough to plot three-dimensional plots. Usually three-dimensional plots, it is very hard to plot. And even for algorithms to work on a three-dimensional, it becomes hard. So what you're doing, you're taking a three-dimensional and you're compressing them into two-dimensional. You're taking three dimensions and compressing them into, you're taking three columns and compressing them into two columns. You're compressing them. That is what this PCA does. What PCA does is, you take 100 columns. Those 100 columns can be compressed into some like 100 can be compressed like 60 or 70. You can compress them. Compression is possible. That's what I mean. You can compress them into less dimensions. If you have cloud of points floating in 3D space, PCA finds the two best angles to look at it so that you can see the most spread. Example just. So then we store that into another data frame. Not agglomerative cluster. Clay means cluster. I'll be again using clay means cluster. Yeah, you can see here. Now instead of showing annual income and spending amount, it is showing as principal component 1 and principal component 2. Why? Because the columns have changed now. I can even remove this too. Yeah, this is PC1 and PC2. So three columns are converted to two columns. Again, why we are learning PCA? Because in future also, if you are working on a project or anything, and if you have more number of columns, more feature columns, and if you want to compress the more feature columns into two columns or something like that, then we use PCA for it. PCA can convert different number of dimensions to less number of dimensions, usually two dimensions. Yeah, any doubts till here? Okay, so that is what all PCA for. I think we are almost at the end. I've taught you everything related to unsupervised. Agglomerative, K-means, StandardScaler, silhouette, PCA, dendrogram, linkage. All are done. Anything I'm missing? I'm just thinking. Mm, naming the clusters. This is one of the thing that most of the people forget. Even people who are doing bigger jobs in ML also tend to forget naming the clusters. You cannot just leave the clusters to be 0, 1, 2, 3, 4. When you're closing anything, you have to name the clusters. Now comes one of the most important steps, and again is often forgotten in students when doing projects, is naming the clusters. Segment names. Oh, no, dictionary. 0. What 0 represents? 0 represents low spending, low income, low spending. Low income, low spending. 1 represents high income, uh, high spending. 2 represents low income, high spending. 3 represents high income, low spending. 4 represents moderate income, moderate spending. We segment clusters.map segment names. So now what happens is, when we have this 0, 1, 2, 3 and all, right, that we have created on the top here. Instead of getting a 0, 1, 2, 3 and 4, now we get the actual names, like what is 0 represents, what does 1 represents, what does 2 represent. We come to know about it now. Mm. Yeah, finally whatever we are gonna store it, we are gonna save the output. Finally we save all our results. Df dot we are going to save it into a csv, Mall Customers segmented dot csv. Yeah. Print project is complete. And finally I just want to see the head of the printed data. Print df customer id annual income spending score and segment dot head. Okay, it has been saved and this is the data. Mm, let's see it, where it is stored. Is it stored in the same place? No.
Your current working directory, usually that's what it's saving for me.
Right. All IPY and B.
Okay. Maybe default locate. What could be the default location? Probably like I'm seeing it says content also can be the default.
Oh, right. Correct, Kamala. Thank you.
Okay. Okay.
Yeah, it's in content.
Content, yeah. The default is content. If you specify, either it will be in the file where you have your IPNB or content.
Nice. Thank you, Kamala.
Yeah.
Yeah, so we have successfully saved our outcome after clustering. So here you can see every person show 100. Yeah. So every person now is categorized into one or the other segment. Male, for example, customer ID 1, age 19, annual income 15K, spending score 13. K means cluster, he belongs to the fourth group. And in agglomerative cluster algorithm also, he belongs to the fourth group. And segment, what is this fourth group mean? He has a moderate income, but he has a moderate spending also. So his income is average, his spending is also average. Let's take a third female, 2016K, spending score is 6, but why it is, oh, moderate spending, moderate income, moderate spending. She's getting average, spending average. So yeah, like that you can see here. Let's take this one, low income, high spending. The income is 37K, but the spending is 75. Means he's spending 75% of his salary. So that is high spending, but his income is low. Like that, we have categorized everyone into different sections. And this is what unsupervised learning does for us. So to summarize, no. Before summarizing, this is the deliverable. This is what we are delivering with this project. A data science project is not complete when you finish training a model, because the training of the model completed here, where not PCA, here. The training of the model completed here. It is completed when you deliver a meaningful response with the output being saved in a format that someone else can use. Then only we say a data science project is completed. In a real job, this CSV file might be handed to the marketing team. I mean, in reality, that is what happens. You will be submitting this CSV file to the marketing team or the management team, and they will be loading this into a dashboard or connecting to a CRM system to trigger targeted campaigns, targeted public publicities, advertisements and all. So to summarize what we have built today, we started with 200 unlabeled customers, applied k-means clustering, validated it with elbow method and Silhouette score, compared it with hierarchical clustering, visualized the structure using PCA, and ended with clean labeled exportable dataset of customer segments. And this is what a complete unsupervised learning pipeline from raw data to a business output looks like. And the same code what I've done also, you can use it for any unsupervised learning project. Not only this, any data, but change the column names. So yeah, any doubts in this entire project or unsupervised learning or anything that we have covered today? Okay. Yeah, then that is
I have
all
a
for.
question,
Yeah,
Manish.
yes, come.
Are there any other clustering mechanic, like other clustering algorithms, apart from the ones that you used, that could be used in, like, in other modeling, in other learning purpose?
Uh,
Because I've only heard k-means clustering. I think another one is, density based, some of the DBSCANs and all.
the most widely ones are always k-means, hierarchical, DBSCAN.
Okay.
And there are other 6 families. I mean, I'll show Wikipedia, but before that, from what I know, you can divide clustering into 6 families. 6 families or 6 types. Usually, they call 6 families. Family 1 is centroid basis. Centroid based. Centroid based algorithms, how they work is groups points around central points. These are the examples of k-means, k-medoids, k-medoids, mini batch k-means. Some of the examples of centroid based algorithms are k-means, k-medoids, mini batch k-means. Second family is connectivity based. Connectivity based. Here in connectivity based algorithms, they merges or splits group by distance. Based on the distance, they do the clustering. Example of connectivity based is hierarchical, agglomerative, divisive. The ones that we covered today, I thought of covering the first main important two ones, centroid and connectivity. These two we have covered today. K-means, agglomerative. Third one is density based. These groups, algorithms of density based groups is dense regions and flags sparse one as noise. Some of the examples of density based is one that you said. DBSCAN is an example of density based. There is one more thing called HDBSCAN, HDBSCAN and optics. These three are examples of density based. Fourth one is distribution based. Distribution based. Here in distribution, the grouping happens on the probability of belonging to distribution. Based only on the probability of something to be on a group, it groups them together. And the classical example of distribution based is GMM. GMM stands for Gaussian mixture models. GMM. I'll show that these all in the Wikipedia now. GMM is an example of distribution based Gaussian mixture models. Fifth is graph based. It uses graphs distances between points. Connectivity based uses normal distances. Graph based uses graph distances. There is a small difference between them. And some of the example of graph based algorithms are spectral clustering, affinity propagation. Affinity propagation and spectral clustering are two classical examples of graph based. And the last one is compression based. In compression based algorithm, it reduces the dimensions first, then clusters. PCA is one of the algorithm, like an example of compression based. And one more example is deep embedded clustering. These are the 6 different types of algorithms families we have in clustering. And let me show you unsupervised learning algorithms. There are a lot of algorithms. Even I don't know all of them. I'll be very honest. I know only few of them. Like K-means, hierarchical, DBSCAN. Mean shift I don't know properly. GMM I know. I also didn't learn all of them.
Okay. Yeah, no, because I've been only hearing a lot of K-means, DBSCAN, these clustering. So I was wondering if you know other.
Yeah, learn only the best ones, widely used ones.
Okay. Thank you.
Yeah. Where are the 6 families? Unsupervised learning. 6 families of clustering. Yeah, 6 known types of. Here are the 6. Centroid based, connectivity based, density based, graph, distribution, compressed based. Here in today's class, you have seen algorithms of centroid based, that is K-means. Connectivity based, you learn agglomerative. Connectivity, you learned agglomerative. Compression, you learned PCA. Yeah, I did not cover all, but these are the widely used ones. Yeah, all 6. Thanks, Kamala, for asking. Otherwise, I would have never explained this 6 families.
Yeah. No, even I did not know. So it's nice to learn.
Yeah, I shared this link. Yeah. So yeah, please go through over the yesterday's class. Today's class is very simple. You can, I mean, easily you can just by looking at the code you will understand for sure. But yesterday's one is a bit complex. Please go through it during the weekdays. If any doubts you have in any of the time, please message me and I'll reply back. Yeah, still any doubts anyone in this class on anything?
This was easier compared to yesterday, so
Yeah,
good follow. Yeah.
yeah. Uh, okay then. Yeah, but please, if any doubts from yesterday class, please let me know. Now we all then take care. See you all in the next class. Next class is going to be on deep learning.
Thank you, Monish. Have a
Thank
good
you,
one.
Kamla. Yeah, bye
Bye.
then. Bye everyone.